Everybody. This is the second video I promised I'd do. So, yeah, just gonna run through a few more story problem examples. Let me try pulling up. Make sure. Okay, so I left off on the last video finishing number 6. So the next one I'm going to talk about is number 8. Now number 6, actually I'll scroll back. Well, 7 is about the same thing pretty much. But number 6 deals with like a mixture problem where they give you a table kind of like filled out for the most part, and just kind of introduced to the idea of using one of these tables to help you solve. Now, you don't necessarily need to use a table every time. So if you look at number 8, number 8 doesn't give you a table to work with, so I'm going to try to do number 8 without a table. And so I will be consistent though with how I started all of these story problems. So if you watch the other video, you should have noticed that every story problem I start by figuring out what the goal is. What is the end goal? And let's define our variables right away. So that way, once we solve for our variables, we know exactly what our numbers really mean. So a lot of times the goal of the problem is usually found at the end where they ask you to do something or tell you to do something. So in this question, I guess it's still being shared. They ask for what amounts of each should be used. Well, all right, I'm gonna probably have to read the problem a little bit more to figure out what they're talking about, but all right, pure acid is gonna be added to 10% acid to obtain a new solution. That's blah, 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 blah. Okay, so what they're asking for is how much of the pure acid and how much of the 10% acid. So I'm gonna just right now define my variables to answer those two questions. And I will stop sharing now. So, oh shoot. I'm on a different computer, so my setup's a little different. Make sure I can see what you guys are seeing. All right, so so they want to know how much pure acid and how much 10% acid. And actually those little boxes kind of help me, they kind of help set up what my variables should look like. So I'm just going to use X and Y. So X, I'm going to call liters, because that's the units that they're using in Pearson there. Liters of pure acid. And then Y I'll call liters of, now they're calling it 10% acid, which is obviously, that's what it is. But I find it kind like sometimes it's easy to lead to some confusion if you put numbers inside of like a definition for one of your variables. So if you're basically, it's easy to confuse yourself if you name one of your variables using a number. So, because, ultimately your variable's gonna have some numeric value. And so I think it's easy to get confused when you have numbers defining the number you get later on. So anyway, I'm going to avoid saying 10% solution, and instead I'm going to call it the weaker solution. So solution. A little bummed my phone doesn't seem to have as good a service as the last time. I'm gonna pause my recording here and see if I can get. All right, I guess I am hooked up to my Wi-Fi, so I'm just gonna have to try to be careful about making sure it's close enough. So anyway, so we've got X is liters of pure acid, X is gonna, or Y is gonna be liters of weak acid solution. So still has acid in it. It's just the weaker solution. So I'm going to try to solve this without a table. Now, granted, I'm not going to guarantee I'm not using a picture because I taught geometry for quite a few years, so I always had a mantra that where I would say, "When in doubt, draw it out." So I love to draw pictures when I'm stuck or if I'm confused or if I don't know where to start. So going to try to draw what I think I understand is going on. So we've got two containers. So this first one has pure acid in it. And they're not necessarily, well, yeah, they're not necessarily going to be the same size container because we're probably not going to use equal parts of both of them. And just draw them in different sizes. And maybe the pure acid ends up being less than the weaker one. I not totally sure, but just to kind of drive the point home that they're not going to necessarily be the same size or same volume. So let's say this jug represents the jug. So I'm going to put some, there's a spout on it where it can pour out and a handle. So these are two jugs with some acid solution in them. And so the total volume of this jug is going to be, so if we're talking pure acid, the total volume is, we define it up here as X. And then our weaker one has a total volume of Y. And so I'm going to start by looking at the weaker one here. Now, again, number one from this homework set is actually a great place to start before you do these because it helps accustom you to this next thing that I'm about to do when it comes to figuring out how much pure acid is in each container. So the weak stuff we know is 10% acid. Now, I'm no chemist, so I don't really know how acid works. But I'm just kind of imagining, like, what if it's chocolate milk? Instead of acid, let's just think of chocolate milk instead. You pour syrup into chocolate milk, you mix it up, and it's mixed together pretty evenly for a certain amount of time. But if you let it sit for too long, then all that chocolate syrup sinks to the bottom. So I'm just going to imagine the acid, works the same way with this. So let's say all this acid settled to the bottom. Now, the 10% tells us that however many liters there are here, so let's just pretend there's 10 liters here. So if there were 10 liters here, then 10% of those, so this is your 10% right here, 10% of those 10 liters would be acid. So 10% of 10 is just 1. So let's say, so again, do another practice number. If it were 20 liters, 10% of 20 is 2 liters. So the pattern there is that we always multiply this percent as a decimal by the total volume that's there. So, so in other words, whatever Y is, whatever that total volume is, I want to multiply that number by 0.10. That'll tell me how much pure acid is sitting in the bottom. So this thing, I'm going to call 0.10. I'm just going to say 0.1Y. So that's how much acid is in the bottom. And then the pure acid, now they didn't give us a number here, so it's easy to get confused at first, but if we think about pure acid, the percentage of this bottle, if it's pure acid, that means there's nothing else in there. So there's only acid in there, which means 100% of it is acid. So we're going to be consistent. Then 100% as a decimal is 1.00 times X. That tells you how much acid is in there. So in other words, whatever the total volume is, that's how much pure acid is in there as well. So this problem is kind of like a special case because of pure acid part. But I still think it's a good opportunity to try to solve it without a chart. So anyway, so as far as acid goes, we've got 0.1y coming from the weak stuff. That's pure acid. 0.1y is pure acid. Whatever X is, that's pure acid. When we mix these two containers together, so these are going to get mixed together into another container that's obviously bigger than the both of them. Mixing them together, let's see, what did the problem ask for? Problem wants the final container to be 54 liters at 20%. So this whole thing, 54 liters at 20% acid. So again, if all the acid settles to the bottom of this thing, 20% of it, so acid is going to take up 20% of the 54 liters. Now, we actually have a number for that. So the amount of pure acid in this final product is simply going to be 20%, aka 0.2 of, which means multiply, 54. So 0.2 of 54, I'm doing this in my head, 5.4 times 2, 10.8. So we need there to be, so out of the 54 total liters, or for one thing, it was chocolate milk. So if we have 54 liters total of chocolate milk, then we need 10.8 of those to be the chocolate syrup. So just replace chocolate milk with the whole solution, and then chocolate syrup, replace that with acid. So anyway, maybe that's helping, maybe that's not helping. But anyway, so we need there to be a total of 10.8 liters of pure acid that's in this thing. So remember, we're getting pure acid from X, we're getting pure acid from 0.1 of Y. Those two amounts of pure acid are going to add together to get the 10.8. So maybe the chart would help you at this point. Maybe you're doing better without the chart at this point. I don't know. But so we know that pure acid from X plus the pure acid from Y, well, from the weak stuff, has to be 10.8 liters in the end. And then the other equation, because if we have two variables, that means we need two equations. The other equation has to do with just the total amount of volume there is overall, everything all together. So this 54 liters is going to be a result of taking the total of X plus the total of Y. So, just total volume of the pure stuff plus the total volume of the weak stuff. That's just X plus Y. Again, if you're not sure, think about the units you're working with. So we know X is in terms of liters. We know Y is in terms of liters. And so if we add liters and liters, we should just get liters back. Same thing with the acid idea. If we're adding acid with acid, then we want pure acid when we're done. Well, that means we are going to get pure acid when we're done. So that should help you hopefully match up what goes with what. So now we're at a point where we have a system we can solve. I would actually say substitution or elimination are probably equally as convenient. And I think I did the last one. I think I did the last one with I did the last one with elimination. So I'm going to do substitution with this one, just to give everyone some exposure to both methods. Now, because I've done this for a while, I kind of know how to do this strategically so I can avoid some nasty numbers. So I'm going to solve this, the second equation. I'm going to get X by itself because I know that the coefficient of X up here is 1. So being strategic, I know that's going to be easier for me. If you solve for this X or this Y, you should be fine still. but I'm going to solve for this x here. That means I got to subtract y. So x equals 54 minus y. I'm going to replace the other x with this 54 minus y. So this equation, the first one, is going to become 54 minus y. So I replaced this x with 54 minus y, which came from here. And then there's still a 0.1 y existing there, and then that's got to equal 10.8. So now we have an equation in one variable that we can solve for y. So we've got -1 plus 0.1. These are my like terms. The -1 plus 0.1 is going to be 54 minus 0.9y, 10.8. I got to subtract 54. Some people might get freaked out when they see some negatives appear, but oh dear, I could do this in my head, but I not dork this up. So 10.8 minus 54. I always make mistakes when I'm under pressure. People are watching, so not that I don't make mistakes when people aren't watching me, but okay, so yeah, anyway, don't be freaked out by the negatives. As long as your final answer makes sense, then that's all that matters, because guess what? We're going to divide by a negative as well, which should make everything positive. Negative 0.9. So y ends up being positive 48. And my cat is saying hello to you all. Y ends up being positive 48. And to get x, where were we at? We had an equation up here. Sorry if you guys can't see, I wasn't able to see my screen for a little while. So here's my work here, subtract 54, divide by negative 0.9. Got 48. And again, that's liters. And if we look back up here, y was the weak solution. And so, which kind of makes sense because we're ending up with a solution that is at a rate which is closer to the weaker one as opposed to the stronger stuff, which was 100%. So we're way closer to the percentage of the weaker one. So it makes sense that we would need more of this one to dominate the stronger one. So just some things to think about that might help your answers make sense, or help you decide if your answers don't make sense. So now we just need to find x. Sorry, I'm making this longer than it needs to be. And the easiest way to find x is probably the second equation where we have just x plus y equals 54. You could use that other one as well. That'll work just fine, but I like to avoid decimals if I can. So x plus y equals 54. We know that y has got to be 48. So subtract 48, and that's 6 liters. If you are worried about it, then you can plug these two values back into the equation you didn't use, and they should still work. So that's the nice part about systems, is you have a way to check to make sure that you did it right. So then just make sure you interpret your answers correctly. So x is the strong stuff, 48 is y is the weak stuff, and so now you know what values to input for each one. So that's solving one of these mixture problems without a table or without a chart. For some people that might make more sense. Some people might like the chart better. You obviously get to choose what method is going to help you be most successful. So, so that's that one. Let's see. I had another one I wanted to try. Yeah, so I'll just run through the setup of this next one. Share my screen. I guess I better do this. All right. So This next one is it is giving us a chart to look at least to start us out. And but it's not a mixture problem now. It's looking at like, well, I guess you could think of it as a mixture problem because we're mixing together two different things to make like a Chex Mix basically. So party mix, whatever, same thing in my book. You're adding nuts, cost blah blah blah, and cereal, the costs blah blah blah. How much of each? All right, so let's see here. That automatically is jumping out as like the goal of the problem. So before I get any farther, I want to start defining my variables, like X and Y. You can use different variables too if you'd like if you'd rather use N and C or something like that for nuts and cereal. So X, I'm going to use for the nuts. And so it looks like the question is saying they're $2.50 per kilogram. So that implies that my my nuts are being measured in terms of kilograms. So kilograms of nuts. Make sure you put units in your variables because that will help you remember what you're talking about. Otherwise, it's easy to confuse like, oh, did I find the price per kilogram or did I find kilograms? So make sure you put a unit in there so you know exactly what you found. Don't just write nuts because then you don't know what about the nuts. Is it the price or is it the weight? So that's why units are important. And Y can be kilograms of cereal. And so actually, well, let me make sure that the table they have is doing that too. So let's see. In the table, looks like they put X in the slot for kilograms of nuts and then Y in the spot for kilograms of cereal. So they're matching ours, so that's good. Probably a good thing to look at that before you write them down. But anyway, so we got that already set up. And then the table, kilograms. The left column is total kilograms, middle column is price per kilogram, and the right column is total value in dollars for the whole thing. So they already told us that nuts, cereal, and then the mixture. So nuts are going to be X, cereal is going to be Y. Sorry, my camera is really terrible right now. And then the total kilograms of the mixture, so let's see, I didn't even read that far, but I bet you we can find it. Total kilograms of the mixture. All right, so how much of each should be added to obtain 60 kilograms of a mix? So that tells us what goes in that slot. Put a 60 there. And then they did fill the middle column in for us, but it should match with what it tells us. So the nuts cost $2.50 each. The cereal costs $1 each for each kilogram. And then the mixture is going to be $1.80 for each kilogram of the mixture. And so if we think about what's going on here, you're going to pay $2.50 for each 1 kilogram. So if you have 2 kilograms here, you're going to multiply this $2.50 by 2 since you're paying for that $2.50 twice, basically. So moral of the story, the pattern is that whatever your total kilograms are, you want to multiply that by the price per kilogram. And that'll give you the total price for that bag. So what I'm going to do here is I'm going to say X times $2.50, or probably a little easier to say $2.50 X. And then same thing here, $1 times each kilogram of Y here. So 1 times X, or sorry, 1 times Y. Granted, you can simplify how you write these, like we don't have to write all these zeros that are at the end. And then 180 times 60. Now, if you want to write it as 180 times 60, you can do that, but we can actually solve that. So 1.8 times 60 is 108. Come back. 108. And so now our table's completed. And if you watch the first video, then this is going to be consistent with how the table worked in that first video as well. Our first equation is going to come from looking at what happens in the kilograms column. So remember, thinking about it, kilograms plus more kilograms needs to result in a total number of kilograms. So this is our first equation right here, x plus y equals 60. And then doing that with rates doesn't actually work in the same way, because rates are not like an actual amount, so it doesn't really work with rates so much. But if we look over here, it does work if you think about total price. So total price of nuts, so dollars of nuts plus dollars of cereal needs to be total dollars for the mixture. So 250, which I'm just going to write 2.5, x plus 1 times y, so I'm just going to write y, equals that total 108. So that's kind of an expensive purchase there if you wanted to buy those 60 kilograms, but maybe you're running a store or something. Anyway, I'm getting off topic here. Again, elimination or substitution are probably equally as efficient, I would say. So use whatever is preferred by you, whichever method you click with better. To save some time, I'm not going to go through and solve with elimination or substitution, but if you need to refresh on those, then I would encourage you to watch some lesson videos from sections 7.5 and 7.4. Those will do a good job of giving you a run through of elimination and substitution if you need some more practice with those. So 7.5 is elimination, 7.4 is substitution. If you need some help with those, I would check those out before you take your midterm. Otherwise, yeah, I'm just trying to help with the story problem part and avoid making this video longer than it needs to be. So I'm not going to finish solving this, but granted, I probably could have had it solved when I finished saying all that. All right, so I said, oh geez, I just realized I hadn't stopped sharing this whole time. Hopefully you could still see. Oh, you know what? I just realized. All right, I'm just gonna show, I just realized that you guys couldn't see my phone at all that whole time. So I'm just gonna run through a quick summary of what we just did. So again, X was kilograms of nuts, Y was kilograms of cereal. We reflected that in our table here. And so total kilograms, we put the 60 here to represent the total kilograms of the whole mixture. And so that gave us our first equation, because kilograms of nuts plus kilograms of cereal should give us a total number of kilograms overall. That's where our first equation came from. They gave us the price per pound for all three of these, so we didn't really need to fill any of that in. And again, you can't really add the rate column together like we do the other two columns, because the rates are not like a total amount. So the whole idea of adding them together to get that final rate doesn't work the same way. And then the total price, so that's a total amount. It's just in terms of dollars. So the total price of the nuts you're using plus total dollars, let me say it again, total number of dollars from the nuts plus total number of dollars from the cereal needs to give you a total number of dollars for the whole mixture, which we said was going to be 108, since we need to take $1.80 for each of those 60 kilograms. So we multiplied those two together. That's how we got the 108. Now this third column, again, we're dealing with a total value. So dollars plus dollars should give us a total number of dollars in the end. So that's our second equation right here. And again, I'm not going to solve this because this video is already pretty long, and I know you guys have Your time is precious. So hopefully this at least helps with the solving of story problems and getting set up. And then the solving of the systems should hopefully be, should have been practiced enough when you did 7.5 and 7.4. If you need to go back and look at those, that's totally okay. So anyway, that's that one. All right, let me see. We were gonna look, said maybe possibly number 11. Yeah, I'll get number 11 set up real quick. So, and to avoid the same issue we had before, I'm not going to share my screen. I'm just going to do it the hillbilly way here and show my phone here on the screen. So, all right, so the problem says a train travels 200 kilometers in the same time that a plane covers 700 kilometers. The speed of the plane is 20 kilometers per hour, less than 4 times the speed of the train. They wants to find both speeds. So the goal of the problem is to find speed. And obviously, when they say both speeds, they mean speed of the train and speed of the plane. So that's the first thing I'm going to write down. And let's see, the table they already got started for us. Let's see, X and Y. They're putting in the R column. R should be rate, and rate in this case is the same as speed. So, yeah, so they're calling X the variable for train. And since we're talking speed, let's see, they're saying kilometers per hour. So X is going to be kilometers per hour for the train. Then Y is going to be kilometers per hour of the plane. We got that. They did get the table set up for us. And they even put the formula up top. They're saying that rate times time equals distance. It might ring in your brain more familiarly as distance equals rate times time. This is saying the same thing. So train, plane. We really only need 2 columns here. So let's fill some things in. So we've got X for the rate of the train, Y for the rate of the plane. Distance, they said for the train was 200 kilometers, and they actually filled that in for us. The plane covered 700 kilometers. Now, they said that the time is the same. So the train traveled 200 kilometers in the same amount of time. So what that means is I can actually, say these are going to be this. I could put a T here, but instead what I'm going to do, sorry, I'm trying to think of the simplest way to explain this. If you want, you can put a T here, and then now these aren't going to be your 2 equations because you only have 1 variable in each. But what these are saying is that X times T is going to be 200, and then Y times T is going to be 700, because remember, we're doing rate times time equals distance, rate times time equals distance. Now, to help us out here, let's read what the rest of the problem said. So, speed of the plane. So that speed of the plane, that is Y. Remember, where Y is in the rate slot for the plane. So Y is, I'm going to write this down as I read it. So Y equals, so Y is 20 kilometers per hour less than. So that means I'm subtracting 20 from something, and it says I'm taking 20 less than 4 times speed of the train. So speed of the train is X, so 4 times that is 4X. So there is one of our equations we want, because we have one equation with 2 variables in it. Now, granted, these equations aren't very helpful because there's a third variable that we don't even care about. So what I'm going to do is, since this time is the same for both of them, let's get t by itself. So that means this time equals, if I divide by x, the time traveled is going to be the distance divided by the rate. And then the time that the plane traveled is going to be 700 divided by its rate. Now remember, they traveled the same amount of time. So whatever we get from doing 200 divided by the train speed is going to be the same as 700 divided by the plane speed. So that means 200 over x equals 700 over y. That's our other equation. 200 over x equals 700 over y. Now, I hate fractions. Most people do too. Granted, they do make your life simpler in a lot of cases, but in this case, we are able to work around them and not have to use them. So what I'm going to do is I'm going to multiply by the denominator, because that's what's causing the fraction to occur in the first place. So I want to undo this division. So I'm going to multiply by y times by y, but I have to do the same on both sides. And then within the same step, I'm going to do the same thing over here to get rid of this x. I'm going to multiply by x over here to undo the division of x. But that means I also have to multiply by x on the other side to keep my equation balanced. So what I end up with is y times 200, aka 200y, equals 700x. And so at this point, this equation and this equation are the two equations in my system. I would strongly encourage substitution to this point because you've already got one variable isolated. And so then you can just substitute this y down here with the 4x minus 20. So 200 times 4x minus 20 equals 700x. So I'm not going to finish solving that. Again, if you need some help with solving by substitution, go check out section 7.4, and there should be some videos in the e-text for you. But so this is probably the hardest part of that problem, is getting to this point, and then hopefully the rest is pretty straightforward. So I'm going to stop working that problem there. And then I also thought 13 was good to look at. So last question I'm going to look at here, number 13. So in his motorboat, Bill Ruberg, the specific name, nice to meet him, travels upstream at a top speed to his favorite fishing spot, a distance of 24 miles in 2 hours. Wow, good for him. Oh, he's got a motorboat. He's not actually paddling. Okay. So I like to draw things out as I go with this kind of stuff. So he's traveling a river. The current was flowing in one direction, obviously. And so actually I'm going to put the arrows current's going in a certain direction. So in the boat, here's his boat, traveling upstream, top speed, favorite fishing spot. He's going this way. Went a distance of 24 miles. Let's say he started down here. And then to get to his favorite fishing spot. And that was a total distance of 24 miles in 2 hours. Returning, he finds that the trip downstream, this is going this way, going downstream at top speed only takes an hour and a half. Now, they didn't mention the distance, but if we use our common sense here, he's probably just going to end up at the same spot he started from. So that should be the same distance, unless somehow the earth opened up and stretched out somehow while he was gone. But so that's going to still be 24 miles going downstream. All right. They want us to find the rate of Bill's boat and the speed of the current. So Bill's boat is going to have a certain speed when there's nothing acting on it. So if it's like in still water, then that's what his boat's top speed is at. That's what they're asking for. And then they also want to know the rate of the current. And so they did help us out a lot, and they told us what X and Y are going to be. So X is rate of the boat in still water. Y is rate of the current. Let's write those down. X is going to be, now I'm going to put a unit in there so I know exactly what I'm talking about. So we're traveling miles measured in a time of hours. So naturally that probably means we're talking miles per hour. And actually that's what Pearson's asking for here too. They want it in terms of miles per hour. So miles per hour of the boat. And then Y is miles per hour of the water or the current, whatever you want to say. Now they did start a table for us. And I would probably encourage you to do that for these types of problems anyway, but you could still use a picture here. So again, we're using the distance, rate, time idea. So rate times time equals total distance. So boat, current. And so if we, now, again, not all of us are physicists or whatever, but if you think about how this should work, if there's no current, then his boat is going to go X miles per hour. But as soon as you throw in a current, then when he's going upstream, that current is going to slow him down. It's going to take away from his boat's speed. So that's why in this table, they're expressing the rate going upstream, which that's actually what I want my table to say, not boat and current, upstream and downstream. So the rate, the actual rate going upstream is not going to be X, it's going to be X minus whatever the current rate is. So X minus Y is what the boat actually travels going upstream because it gets slowed down by the current. The current is literally taking away from the boat speed. But when you go downstream, the current's going to help. It's going to add to the boat speed. So that's why we have X plus Y in that slot. And then if we look at what we have here, when we went upstream, it took 2 hours for time. And yeah, the total distance was 24 miles. Now going downstream, the total time was actually 1.5 hours. So I'm going to put a 1.5 there. The distance was actually the same. So I'm going to put a 24 there again. If we think about rate times time equals distance, that's what we're going to do with these 2 rows here. This whole rate, notice I'm putting parentheses around it, times the time equals this distance. So I'm going to say X minus Y as a whole times 2 equals that 24 miles. And then the X plus Y as a whole times the 1.5 is going to be 24 again. And then those are your 2 equations. It looks a little scary right now because, you know, we don't have, it's not like in standard form right now. So all you have to do is really distribute the 2 and the 1.5. So what this actually turns into is we end up with 2x minus 2y equals 24. Again, I'm just distributing the 2. We're not multiplying the whole equation by anything. I'm just distributing that 2 through. And then the second equation becomes 1.5x plus 1.5y, 24. At this point, I would think that elimination is probably the best bet here. If you're a big substitution person, you can go for it. You could probably solve for one of these variables in the first equation and not really get any decimals or fractions. Yeah, you might be able to pull that off here too, in the second one. But anyway, elimination is probably the quickest. And yeah, I'm not going to solve it, but if you need some help figuring out how to do elimination, then go check out section 7.7. There's some good videos and examples in the e-text, or if you want to just review the homework, you can do that too. So anyway, that's all I had for examples to do from this section. Yeah, I hope this was helpful. Thank you to all who reached out and gave me something to teach about finally. So Good luck on your midterm, and don't hesitate to reach out to me if you have any questions. Just a reminder that I can't guarantee being able to help you over the weekend, so you have basically until the end of the day, Friday, to try to email me or try to set up a meeting. So anyway, good luck and enjoy the rest of your week.